It was not supposed to be there. A smudge of light. Red. Faint. Almost nothing. But the numbers didn't lie. Somewhere behind that faint red smudge sat a galaxy, fully formed, packed with stars, spinning in an orderly disk. That should have been impossible, because according to everything astronomers thought they knew, this galaxy was born too early, too big, too fast. It shouldn't have had time to exist. This is the real story of how the James Webb Space Telescope looked back toward the beginning of everything and found something that broke the model of the universe itself. July 12, 2022, Greenbelt, Maryland. NASA's Goddard Space Flight Center released the first full-color images from the James Webb Space Telescope to the public. Among them was a single frame that would quietly upend cosmology within 18 months. SMACS 0723, a deep-field image showing thousands of galaxies packed into a patch of sky no bigger than a grain of sand held at arm's length. At first, the reaction was pure astonishment at the beauty of it. Sharp spirals, golden arcs of gravitational lensing, points of light stretching back further than any image humanity had ever captured. But within weeks, a small group of astronomers noticed something buried inside the data that had nothing to do with beauty. Some of those galaxies were too old, not old in the sense of being ancient artifacts drifting through empty space, old in the sense that their light had been traveling for over 13 billion years to reach us, meaning we were looking at them as they existed just a few 100 million years after the Big Bang. And they were not small, chaotic blobs of gas the way early universe theory predicted. They looked mature, structured, massive, in some cases disc-shaped like fully developed spiral galaxies similar to our own Milky Way, except they existed at a point in cosmic history when, according to the Standard Model, galaxies should barely have begun to form at all. For context, no instrument before JWST had ever been able to see this clearly this far back. The Hubble Space Telescope, for all its achievements over more than 3 decades of operation, was fundamentally limited by the wavelengths of light it could detect. As the universe expands, light from the most distant objects gets stretched, redshifted, out of the visible spectrum and into the infrared. Hubble could catch glimpses of that infrared light, but only faintly, only at the very edge of its capability. JWST was built specifically to solve that problem. Its mirror, 6.5 meters across, and assembled from 18 hexagonal gold-coated segments, was designed to capture infrared light with a sensitivity roughly 100 times greater than Hubble's. It was positioned nearly 1.5 million kilometers from Earth, at a gravitationally stable point called the second Lagrange point, shielded from the heat of the sun by a tennis court-sized sun shield, cooled to nearly 223 degrees below 0 Celsius, so its own instruments wouldn't drown out the faint infrared signals it was built to detect. It was, in every sense, an instrument engineered to look further back in time than humanity had ever looked before. And within days of its first images going public, it was already finding things that didn't fit. Stay with me, because this is where the story stops being a headline about a beautiful telescope and starts becoming a genuine crisis in physics. To understand why this mattered, you have to understand the timeline astronomers had trusted for nearly 30 years. The universe is approximately 13.8 billion years old. For the first 400,000 years, it was too hot and dense for light to travel freely, a fog of plasma astronomers call the Dark Ages. Only after the universe cooled enough for the first atoms to form did that fog begin to clear. Stars didn't ignite until roughly 100 to 250 million years after the Big Bang. Galaxies, real galaxies with billions of stars organized into gravitationally bound structures, were expected to take hundreds of millions of years more to assemble, growing slowly through mergers, one small clump of stars colliding with another, over and over, across billions of years. That gradual buildup was the backbone of what's called the lambda CDM model, the standard framework of cosmology, built on cold dark matter and a cosmological constant that has successfully explained the large-scale structure of the universe for decades. Under that model, a galaxy as massive as the Milky Way should not exist until the universe is several billion years old. JWST was finding candidates for galaxies that size at 300 to 500 million years after the Big Bang. That's not a small discrepancy. That's a galaxy showing up in the delivery room already the size of an adult. To understand how strange that is, think about the mechanics of galaxy formation the way cosmologists have modeled them for decades. In the standard picture, the earliest structures in the universe were tiny, clumps of gas and dark matter barely large enough to be called protogalaxies, containing perhaps a few million stars at most. These small clumps were pulled together by gravity over immense stretches of time, merging with their neighbors again and again, each collision adding mass, each collision triggering new bursts of star formation. It's a process astronomers call hierarchical structure formation, and it's slow by design. Small things merge into medium things merge into large things. The Milky Way itself is thought to have absorbed dozens of smaller satellite galaxies over the course of billions of years. a process that in some form is still ongoing today, as our galaxy slowly consumes streams of stars torn from smaller companions. Under that model, building something the mass of the Milky Way should take the better part of cosmic history. It should not be finished within the first 500 million years, and yet the data kept coming back the same way. In February 2023, a team led by astronomer Ivo Labe, publishing in the journal Nature, identified 6 candidate galaxies in early JWST deep field data that appeared to be far more massive than current models allowed. One of them, if confirmed, would have contained roughly as much stellar mass as our present-day Milky Way, but existing just 500 to 700 million years after the Big Bang. To put that in perspective, the Milky Way took over 13 billion years to build. The mass Labe's team was seeing in a galaxy barely a 500 million years old. Some astronomers quickly flagged reasons for caution. Redshift measurements from early photometric data, meaning color-based estimates rather than direct spectroscopy, can carry significant error bars. It was possible some of these galaxies were closer, smaller, or dimmer than they appeared, distorted by dust or by an overly bright, compact core mistaken for extended stellar mass. That caution turned out to be justified for some of the objects, but not for all of them. The paper triggered an immediate and unusually public scramble within the astrophysics community. Preprint servers filled with competing analyses within weeks. Some researchers argued the entire sample was an artifact of systematic errors in how brightness was converted into mass. Others pointed out that even accounting for reasonable uncertainty, at least 1 or 2 of the 6 objects appeared to survive rigorous scrutiny, meaning the anomaly, even if smaller than first reported, was real. That distinction mattered enormously. A single confirmed impossible galaxy is not a statistical fluke you can wave away. It's a data point that any viable model of the universe has to be able to explain. The pressure was now on spectroscopy, the only tool precise enough to settle the argument. The real test came when scientists moved past color estimates and used JWST's onboard spectrograph, NIR spec, to measure redshift directly by splitting a galaxy's light into a precise spectrum and reading the exact wavelength shift caused by the expansion of the universe. Spectroscopy doesn't guess, it measures. In December 2022, an international team confirmed the redshift of a galaxy catalogued as GNZ11 at a value of ZPLs 10.6, placing it just 430 million years after the Big Bang, making it one of the earliest confirmed galaxies ever observed at the time. GNZ11 was not just early, it was luminous, far brighter than a young, small galaxy should be, and it showed signs of an actively feeding supermassive black hole at its core, visible as a compact, energetic point of light astronomers call an active galactic nucleus. A supermassive black hole, feeding, already active, 430 million years after the beginning of time. Supermassive black holes are thought to form from the collapse of massive early stars, then grow slowly over hundreds of millions of years by consuming gas and merging with other black holes. Finding one already active this early meant either black holes formed faster than expected, started from far larger initial seeds than predicted, or grew at a rate that broke the physical limits astronomers had calculated for matter falling into a gravitational well. None of those options were small revisions. Each one required rewriting a piece of the story of how the universe assembles its most extreme objects. There is a theoretical speed limit for how fast a black hole can grow called the Eddington limit, a balance point where the outward pressure of radiation from infalling matter pushes back hard enough to choke off further feeding. Black holes can exceed that limit for short bursts, but not indefinitely, and not by enormous margins. For a black hole to reach supermassive scale just 430 million years after the Big Bang, it would need to have started from an unusually massive seed, or fed at rates pushing right up against, or briefly beyond, that theoretical ceiling almost continuously, from nearly the moment the first stars ignited. 12 billion years. That's how long it took our own galaxy's central black hole to reach its current mass. GNZ11 appeared to be running the same process on what looked like fast forward. Then came a new class of object nobody had a name for yet. Throughout 2023, as JWST surveys expanded, including the JADE survey, the Cosmic Evolution Early Release Science Program known as SEERS, and others, astronomers began noticing a population of small, extremely red, extremely compact sources scattered across the deep fields. They nicknamed them, informally, little red dots. At first, some suspected they were simply dusty star-forming galaxies, their light reddened by clouds of gas and dust, the way a sunset reddens as light passes through Earth's atmosphere. But their spectra told a stranger story. Many showed the telltale signature of gas swirling around a black hole at extreme velocity, broad emission lines that, in nearby galaxies, are the fingerprint of an active black hole's accretion disk. If that interpretation holds, the little red dots may represent an entirely new transitional phase of galaxy formation, objects where an overgrown black hole dominates the light output of a still-forming galaxy, rather than the reverse. By mid-2023, researchers estimated that these compact red objects appeared far more frequently in the early universe than any existing model predicted, potentially outnumbering the black hole population astronomers expected to find at that cosmic epoch by a significant margin. An entire hidden population of overgrown black holes sitting at the heart of the earliest galaxies that no simulation had accounted for. Something in the early universe was manufacturing black holes, and possibly galaxies, on a production schedule nobody had written into the physics. What makes the little red dots especially strange is their compactness. Unlike a typical galaxy spread across thousands of light years, many of these objects appeared unresolved even to JWST's sharp optics, meaning whatever was producing that much light was crammed into a region far smaller than a typical young galaxy should occupy. A galaxy that small, producing that much light, glowing that red, it doesn't fit neatly into any single existing category. It isn't quite a normal star-forming galaxy. It isn't quite a classic quasar, the extremely luminous black hole-powered objects seen in the later universe. It sits in a gap between categories that astronomers didn't know needed a name. By late 2023, some researchers had begun referring to the phase informally as an era of black hole dominance, a stretch of cosmic history where growing black holes may have briefly outshone the stars around them, a phase so short and so early that, before JWST, no one had ever caught it happening. By early 2024, the pattern had become difficult to dismiss as a handful of outliers or measurement errors. Across multiple independent surveys, JADES, SEERS, and the Uncover program using the gravitational lensing power of galaxy cluster Able 2744, astronomers kept finding the same three problems repeating. Too many massive galaxies too early, too many active black holes too early, too much structure too early. A 2023 analysis led by astrophysicist Mike Boylan-Colchin at the University of Texas at Austin quantified just how serious the tension was. Using the standard cosmological model, his team calculated the maximum amount of stellar mass the universe should statistically be capable of producing by a given early epoch, essentially a hard ceiling based on how much ordinary matter was available and how efficiently it could form stars. Some of the JWST candidate galaxies appeared to exceed that ceiling, not by a small margin. In select cases, the implied stellar mass appeared to require converting gas into stars at close to 100% efficiency, a figure so far outside anything observed in the modern universe that it functioned less like a measurement and more like a warning flag. Either those specific galaxies were being misidentified, or something about early star formation and galaxy assembly worked in a way no existing model captured. This was no longer a curiosity buried in a footnote. This was a body of evidence with the potential to challenge the foundation cosmology had been built on for a generation. You need to understand what a ceiling like that actually means in practice. It isn't a soft estimate or a rough guideline. It's derived from basic physical bookkeeping. Cosmologists can calculate with reasonable confidence how much ordinary matter existed at a given point in cosmic history, based on measurements of the universe's overall composition from instruments like the Planck satellite. From that total matter budget, and from the observed efficiency at which gas typically collapses into stars in the modern universe, they can calculate an upper bound on how much stellar mass could plausibly exist by any given epoch. When observed galaxies push past that number, there are only a few possible explanations. Either the mass estimates are wrong, or the age estimates are wrong, or the efficiency of star formation in the early universe was dramatically higher than anything observed today, meaning young galaxies were converting gas into stars at a rate the modern universe simply doesn't produce anymore. Each explanation carries consequences. And by 2024, researchers were running out of ways to make the first two explanations account for every anomalous galaxy in the dataset. This is where a controversial idea entered the conversation, championed most visibly by cosmologist Richard Ellis, along with several colleagues exploring alternatives to the standard model. What if the timeline itself was wrong? One provocative proposal, sometimes called tired light or alternative expansion models, questioned whether standard assumptions about the relationship between redshift and cosmic age needed revision, potentially compressing or stretching the timeline in ways that could ease the tension. A separate and more widely discussed possibility came from researchers modeling primordial black holes theorized to have formed not from dying stars, but directly from density fluctuations in the first fraction of a second after the Big Bang. If black holes existed before the first stars did, they could have acted as gravitational seeds, pulling in gas and dark matter far earlier than the standard model allows, kick-starting galaxy formation on a drastically accelerated timeline. It's an elegant idea. It would explain why so many of JWST's earliest galaxies already show central black holes. It would explain why the little red dots exist. It would explain why structure appeared to snap into place almost as soon as the universe was transparent enough to see. But an elegant explanation is not the same as a proven one. Most of the cosmology community has urged caution, not dismissal, but caution. The lambda CDM model has survived nearly every previous challenge thrown at it, from the precise pattern of the cosmic microwave background measured by the Planck satellite, to the large-scale distribution of galaxies mapped across billions of light-years, to the abundance of light elements like helium and lithium predicted by Big Bang nucleosynthesis. A framework with that track record does not get discarded because of a few dozen unusual objects at the very edge of what any telescope has ever observed. Researchers examining the impossibly massive galaxy candidates have found, in several specific cases, that revised analysis brought the numbers back within, or much closer to, what the standard model allows. Some galaxies initially flagged as ultramassive turned out to have their light contaminated by an active black hole, artificially inflating the apparent stellar mass. Others had their redshift revised downward once spectroscopic follow-up replaced the earlier photometric estimate. Astrophysicist Erica Nelson, one of the researchers involved in identifying the original massive candidates, has been explicit that these findings represent a genuine puzzle worth investigating rigorously, not proof that the Big Bang model is broken. The most likely resolution, according to much of the field, is not that the age of the universe is wrong or that dark matter doesn't exist.